All right. So how many people took a look at the previous exams? Just a kind of precursor. Take a look. Okay. No one had time. It's okay. It's only 2 days. Since we started on this one. Okay. So let me pop up this page first. Oh, by the way, I worked on the Omega program myself, and this is the solution. You guys are more than welcome to download it and kind of just take a look at it. Do you want me to talk about this a little bit too?
Yes.
Okay. Yes. All right. So we can do that. Because I think even though the program is already here and you guys can read it anytime you want to, having me to explain it may be helpful. So we'll take a look at that. Okay, this is not the window I want. This is the one. Okay, so this is my implementation of Omega, which does not mean that yours has to be resembling this, but mine is implemented using the same recommended methods as what we talked about last time. So I'll explain it line by line, sort of line by line, Okay, so the first thing I did was to define a set as a 64-bit unsigned integer. I think I talked about this a little bit in class as well, is to make sure that whatever integer type you choose has at least a certain number of bits. So this is the way to make sure that whatever integer type you want to use has at least, in this case, 64 bits, which is more than what you need for your homework assignment. If you don't do this and just use int or unsigned, that's fine, because unless you're using a very small platform. In other words, if you're doing this on an Arduino, then an int is only 16-bit wide. Your Omega program may not run on an Arduino. I don't think it's a major concern, for you guys, but it is important. It's always useful to kind of know what kind of width we are dealing with, especially when the width of the integer is important. So a type def is just basically aliasing. So from here on, the type set is really the same thing as the type of unsigned integer of 64-bit. Okay. The next line, basically just uses a.
What does the T mean? Unsigned 64.
Huh?
T.
Yeah, underscore T.
Oh, underscore. Oh, okay.
Yeah, this is an underscore right here,
that.
and there's underscore T.
Okay.
It's just definitions in stdint.h or standard integer.h.
I thought it was a space.
Okay, gotcha. There's a little underscore. It's really kind of, I guess it's not very visible, but it is there. Okay. And then the next one is defining what is an element. An element is just an unsigned integer from 0 to, in this case, 63. I try to use constants as much as I possibly can. So the first element is element 0. The last element depends on the actual width of size. So I use the operator called sizeof, which returns the number of bytes of whatever is in parentheses. So whatever is in parentheses can be a type specification, but it can also be a variable, or it can be any expression. So I can stick an expression inside, and it will figure out what is the size of the type as the result of that expression. I'm not sure how much of this was actually introduced in CISP 360, but all of these are basic C features and not even C++ features. The next one is an invalid element, because sometimes I need to have a value to specify, hey, this is not a valid element for initialization purposes. Yep.
For both the last element and invalid element, I was wondering what's the purpose of the times 8 minus 1 and
because I'm using the bitmap representation, which means each bit of the 64-bit integer represents the presence or their lack of a particular element. So I can only represent up to 64 elements in one quote-unquote set because of the 64 individual bits in the 64-bit integer. Mm-hmm. So that means if I call the first element 0, because I like to use 0 indexing, that means the last element is going to be the number of bytes times number of bits per byte minus 1. So that would make it 63.
Gotcha.
Yep. And then the invalid element is just one past the actual last element. I'm using a constant here because this way I can just compare to the constants instead of having to remember, oh, 64 is the invalid bit.
Okay.
It also makes the program more flexible. For instance, if you're doing this on an Arduino, but you really only need to have up to 16 elements per set, I can just change one definition. I can change the definition over here. Instead of uint64, I can change it to uint16, and then the rest of the program does not need a whole lot of modification, other than checking the range as the input and so on. So I'm making this program. I'm trying to make this program as flexible as possible. Okay. And also, I define an empty set. An empty set is really defined to be a 0 because it has a type of set, which means this is really a 64-bit integer that is representing the value of 0. Because to represent the value of 0, a 64-bit integer would just be 64 zeros. And a 0 represents that each bit or each element is missing. So we don't have element 0, we don't have element 1 all the way, and we don't have element 63 either. So is that okay so far? A 1 means a particular element is present, a 0 means a particular element is absent. Okay. So this is how I choose to represent a set. And then I use a structure to represent the parameters, which is totally unnecessary, but this does make reading the parameters a little bit clean, because I can just pass a pointer to a struct params, and then I use Scanf, which is kind of analogous to cin, except you specify what you're reading, because in Scanf it doesn't know what is the type of each thing, so I have to specify what we are reading. So %u is unsigned, %d is signed integers. But if you use cin, you don't have to deal with this. Okay, it's just cin greater than the rest. And this part here is just saying is error checking. If I'm not reading 3 things from the input, that means the input is not valid. And if the input is not valid, I return a non-zero value, so that whoever is calling this and say, hey, you're not giving me enough parameters, I'm not going to do a single thing. You don't have to check for that, because I guarantee that the input to your program, when I test it, is going to be valid. So this is stuff that you don't necessarily have to do, but I just like to do things, to prepare for, okay, what if the input is invalid? So we have this one we talked about in class already. This particular subroutine checks whether a particular element is in a particular set or not. It returns a value of non-zero. In this case, it's guaranteed to be a 1, but it is non-zero if the element is in the set, and it returns a 0 if the element is. It returns a non-zero when the element is in the set, and it returns a 0 when the element is not in the set. Yep.
You really don't even need a conditional statement, right? It's going to return 0 or 1 anyway.
I would not need that if the return type is a set.
Okay.
Because it depends on how wide is an int. Because if an int is only 32-bit wide, and the bit mask result has a 1 that is past bit 31, then I'm actually going to return 0, because it's truncating the more significant bits. And that's why I test and return a specific 1 in this case. So to fix this problem, as I suggested, if you change this int to set or uint64_t, then we'll be okay. So the other one, this one here is returning a set itself. I'm adding element E to a particular set. So it's really just the element that we are dealing with, figuring out what is the bit mask of that one, and then do a bitwise OR with whatever set is given to me. So whatever I'm returning here is the original set S, but with the added element E being present in the set. Is that okay? So this is kind of what we talked about before, using bitwise operations and using the bitmap representation to represent the set. This one, instead of adding, this one is removing a particular element, and I realized that this one is actually not needed. So I did not actually need this particular one, except for initializing the first set. So this one is kind of the same thing, except we are removing element E from a particular set, but I'm not changing set X itself. I'm just returning the new set that has element E missing. So whatever you want to do with the result, you can assign it back to S if you want to, using an assignment statement, or you can just use it and pass it as a parameter. So the way to do that is to use a bitwise AND operation instead of a bitwise OR. And this time I'm using the original set, bitwise ANDing with the negation. This is a bitwise NOT of the one single one that is representing the element that I want to remove. So all the other bits will be ones except for the one that I want to remove. And then when you perform a bitwise AND, then I'm preserving all the other bits except for the one that I want to remove, because that's the only one that I'm ANDing with a 0. Everything else is ANDed with a 1, which preserves the original value. Okay. And just to be in the spirit of C++ programming, I use a set iterator, which has a set that I'm iterating over, as well as which element I'm looking at. So this way, it's just a little bit nicer. To initialize the set iterator, I initialize the set itself, and I'm also initializing the first element to be 0. Then I just scan my way over. This particular function is just finding what is the next element in this particular set. Okay, how many people are familiar with the concept of an iterator? It should be covered in cisp440.
It's what we used to keep track of how many times we've gone through a loop, right? Is that kind
right. It's used in a loop condition, so that you can kind of move on to the next whatever item. So in this case, I'm just scanning. I'm starting with E is an invalid element, so that if there's no other element in the set given to me, in the initialization, I would return invalid element. And then to stay in the loop, this is the condition to stay in the loop. So as long as I have not found an element in this particular set, and I have not reached the last element, I have not scanned the last element, stay in the loop. Okay. When I do stay in the loop, this is what I do. Okay, I use the call to check whether a particular element, which is E of the iterator, is actually in the set S. If so, the local variable E is initialized to E as a member of the iterator. In other words, I just found an element in the set, and this is what I'm going to return. So if I do go through line 70, it will turn this particular condition false, because anything that is an actual valid element is not invalid element, and this condition will fail, which means I'm going to get out of the loop, and then I will just return E. If I have not found anything yet, which means this condition is false, then I keep going, because I will do a post increment here. The post operation is to increment E as a member. So I'm basically moving on to the next possible element and say, hey, do we have this one in the set? So I keep doing this until I find one that is actually in the set S, which will make this condition false, or I have scanned past the very last element, which will turn this condition false. But either way, I will get out. And when I do get out, I return E as the actual return value of this particular subroutine. So that's just a very crude way of doing an iterator. I mean, C++ has fancy iterators, but this is what I can do in C. And here we have invocation data. So invocation data is a single structure that represents everything that a particular invocation of the subroutine will possibly need. So let's take a look at omega itself. This is omega. So when I implement omega, I need to know how many trials are left for this particular invocation to deal with, what choices are left for this particular invocation to deal with, and I also need to know whether it is with or without replacement. And I also need a back pointer, and this is what we talked about in a previous class. I need a back pointer so that the current invocation of omega can access all the invocation data of the previous invocations of omega. So it gives me the ability to travel back in time and say, okay, I got here because of the previous invocation of omega, and that invocation of omega has this particular element selected, and then I can go backwards until I get to the end of the entire chain. Okay. So inside each invocation, I deal with the end of the recursion first when there's 0 trials left. In other words, if somebody tells me, okay, say, Jack, I want you to perform experiments. And I go like, okay, tell me how many trials are left for me to do. And then the answer is 0. I go like, woohoo, I don't have anything to do. Well, there's one thing I have to do, because now that all the trials are performed, it means it is time for me to print out what choices have been selected in all the previous trials. Is that making any sense? Sort of? Okay. So I would use previously, which is a pointer to the previous invocation data. And if previously is not null, okay, it means there is a previous. So in that case, I'm going to print out the printable element of the previous invocation. And this is basically the same thing as a cout with a character, except this is the C way of doing it. It's a little bit kind of more convoluted, but I'm very familiar with this way of doing things. Your code can use cout, because you can't use C++ for your program. So that's not the most important part. The most important part is I'm also going backward a little bit more. So each invocation data maintains a back pointer to the one that is previous to it. So the first invocation of omega will be pointed to by the second invocation of omega. The third one points to the second one, the fourth one points to the third one, and so on. So I can travel back in time to figure out, oh, what was the choice of the first trial? Okay, and the second one, and the third one, and so on, except I'm going backwards. When this is all done, I print a single line feed character to end that particular line. That concludes what I need to do when there's 0 trials left. What if this is the first call to omega and I have 0 trials left? It would just print end of line. That's all it's going to do. Okay? What if trials left is non-zero? Now trials left is unsigned, which means if it is non-zero, it is guaranteed to be positive. So if it is positive, then I have this loop here. So inside this loop, the initialization is on line 105 is to set a previous first. Okay, data is mine. Okay, you can look at line 102. Data is a local variable that is a structure, which is equivalent to a object in C++ programming. Okay. So I'm initializing my own previous to be previously, which is passed to me by a recursive call, possibly a recursive call. My choices left is whatever is choices left, as a parameter. And then I initialize the set iterator on line 107. Basically, I'm just saying, okay, these are my choices. Set up the iterator so that I can use the iterator to go through the entire set. So this part is representing the pre-operation or the initialization of the loop. This part here is specifying the condition to stay in the loop. So in order for me to stay in the loop, I'm just going through the choices that I'm given with by the caller of mine and say, okay, what is the next element in this particular set? In other words, what is my next choice? Is that okay? Now, as long as that next choice is not an invalid element, it means, okay, we just found another element in the choices, then I'll go through the loop body. So when this condition is false, it means I have reached the end of the entire set. I have gone through every single element already. And in that case, E is going to be an invalid element, which signifies that I should leave. When E is not an invalid element, I will go through this code here from line 111 to 116. Line 111 is just converting the number 0 to the ASCII code of lowercase a. It's converting the element 1 to the lowercase character b, and so on. In other words, I'm just converting my elements, which are numbers, from 0 to 63 to printable characters from lowercase a to lowercase z in your homework. Is that okay? All right. Now remember, printable element is a part of data. It's an element, it's a member of data, and that data is a local variable. and then when then I do the recursion. In other words, this is basically saying, okay, for this particular iteration, I am choosing this element to be my choice. Okay, so when I recursive call omega, I would tell the next invocation of omega and say that, you know what, I took care of one trial out of the total number, so the next invocation has one fewer trials to deal with, and that's why it is trials left -1. This is a ternary operator. I'm evaluating with replacement first, okay? If it is with replacement, I'm just using whatever choices I have. In other words, I'm not removing the one choice that I'm taking because it is with replacement. Is that okay? So if I have 5 choices to begin with, I'm passing all 5 choices to the next invocation because it is with replacement. On the other hand, if with replacement is false, then I'm going to use this as the parameter as choices to the next invocation, which is making use of a subroutine that we talked about a little bit earlier. It removes the element E from choices. But it's not changing choices itself because it returns a value. And the return value is used directly as the parameter in the recursive call. Is that okay? So I never really have to add the element back because as far as I'm concerned, my choices has never changed. And then the next one is just the 0 versus non-zero of with replacement. It's telling the next invocation whether it is with replacement or without replacement. And then this is the most tricky part. The most tricky part is I'm passing the address of my own invocation data to the next invocation, so that the next invocation can track down 2 things that are important. One is my printable element. Which one have I chosen, as my element for a particular trial, as well as my own previous, so that the next invocation can go through me to go to the invocation that is prior to me. Is that okay so far? Sort of? Okay. All right, so that's the entire omega subroutine. And then the main subroutine, this is the initialization. So if you tell me how many outcomes is from the first trial, this is going to initialize a particular set, so that particular set has all of those elements being present in the set. Okay, if you tell me that there are 10 outcomes, then I will go through this loop exactly 10 times, and then each time I go through this loop, I am adding element 0, 1, or 2, 3, all the way up to 9 to set S, and then S is returned. So this is how I initialize the whole thing, and this is the only place where I need to add a particular element to a set. Are we still doing okay so far with this code? Just the general idea? No? Yes? Okay. So the main program, becomes really simple because the first thing I do is I'm reading the parameters. I really should check whether the value of read param is 0 versus non-zero. In other words, if I were to utilize this correctly, I should have said, as long as this is returning a non-zero, then we do the following, which is calling omega. And if not, we don't do a single thing. And I'm missing a return 0 at the end too, because int is supposed to return an integer. But that's kind of peripheral to this entire program. So the important part here is I'm just using the elements or the members of params here to specify the number of trials per experiment, which is what I read from read params. This is the call to to initialize the first outcome set based on the number of outcomes per trial. This is really just with or without parameters, or with or without replacement, which I read in the previous in this particular read params call. But this is the most important part. The first call to omega has null as the address of data, because hey, this is the first invocation. I don't have a previous. And this is where the track back is going to stop. Yep.
Could you just set its default value as nulled? And just call it as a?
Yes, you can. Yep. You can set the default or yeah, you can set the default value of the last parameter to be null, then you don't have to specify here. Yeah, but it is kind of important to specify the null here to basically say that it stops here. So that's my implementation. And as I said, my implementation is consistent with the discussion that we have gone through in class, like how do we represent a set, how do we perform set operations, and how do we track backwards so that we can say, oh, the first invocation has chosen this element as its choice, the second invocation has chosen this element as its choice, and so on. There you go. All right. So how does this compare to your solution? About the same? Yep.
Yeah, you were like adding the entire set and then deleting off as you were going through and marking them off, right?
Yep.
Yeah, I went through and I flagged them as I was putting them in there.
Okay, that's fine.
So I just did it also.
Yeah, as you're representing it differently. I mean, that's fine.
It's like the same time.
Yep. Any other comments of this particular program? Does it remind you of anything that you did in cisp440, which is huh?
Was it like stacks, kind of? A little bit. It's like you're adding each element and then popping it down, kind of. Just list. Linked list.
It is kind of like a linked list. Yep. So it's a linked list going back in time. Because the last invocation is the one that has to print out the entire thing. So you need a way to figure out what choices has been chosen, in the previous invocations.
Yeah.
So this is just one way to tracking it. The other way to track this is to use an array that you allocate in main, so that you just pass that array, as a pointer, so that each invocation, has an index that says, okay, I'm trial number 3, so I'm going to put a character in the third position of the array. The next one will put a character into the 4th position, and so on, so that the last invocation, just look in the entire thing, put a null terminator, and then print the entire string out. So that's the alternative to do it. All right. Are there any questions about this? No questions? Yep.
Could you run it real quick? I
Yeah.
want to see the output.
Yep, I can definitely run it. So just gcc-g, just in case it crashes, omega dot c. So we run omega. What do you want to test it with? Something that can end in today's class, right?
Yeah.
Because this may not work very well. This will give you 26 to the power of 26. Well, this is without replacement. Yeah, this is with replacement. This will give you we won't have enough time for this one. So let's try. Tell me what you guys want to do.
5 and 3.
Huh?
5 and 3.
5, 3. Okay, 5. So 5 choices for the first trial. 3 trials per experiment, with or without replacement.
With?
Huh?
With
replacement. So there's a non-zero here. So that's the outcome. So this one is pretty easy because it's AAA, AAB, AAC. So it's kind of like printing numbers in base 5. Yep.
Didn't you want us to do it in the reverse order though?
The order is not really important.
Oh, okay.
Yeah, the order is not important because you can put the order pretty easily.
Okay.
Yeah.
Gotcha.
Yeah. The order is not important. It is what you list that is important. Okay. So this is with replacement. If I run the same experiment again but without replacement, this will work too. I can enter the 3 numbers without line feeds. So you can see how this time it generates things a little bit differently. Because the first line is no longer AAA, it's ABC. Because if the first C is actually from the last invocation. So if the first invocation has chosen A, the second invocation cannot choose A anymore because it is without replacement. If A and B are chosen by the first 2 invocations, then the last invocation, the third invocation, cannot choose A or B, which makes C the first available choice. So when you count the lines, okay, you can do that too. So when you look at this and you pipe it to WC, which is word count, 5, 3, and then a 0. It should be 5 choose 3, or 5 permutation. It's the permutation of 5 chooses 3, which is 5 divided by 2 factorial. 5 factorial is 120. 2 factorial is 2, so it should count to 60. Okay, so let's see whether it counts to 60 or not. Yep, exactly 60 lines. On the other hand, if it is with replacement, which means the input is 5, 3, and 1, then it would just be 5 to the power of 3. So that's 25 times 5, which is 125. Okay, so we press the Enter key, and in fact, it has 125 lines. In other words, this program is, I assigned this as a homework assignment to help clarify, what is the concept of with and without replacement, and why the equation of why the formula of permutation works the way it does. Okay. So are we doing okay so far with this? Okay, cool. All right. And I think this is probably why cisp440 is a co-requisite of this class, because working out algorithms like this needs the basic understanding of data structures. All right. So getting back to discrete probabilities, I think last time we kind of concluded already with the binomial distribution, or the binomial theorem. So we went through this whole proof, and then the conclusion is this little part here. If I have n coin flips and I look for m heads, p is the probability of landing on a head, q is the probability of landing on a tail, then this value, this expression, tells me the chances of having m heads of n coin flips with p as the probability of landing on a head. Is that okay? Okay, so now we go back to the previous exams and try to figure out the answers of each one. I'm going to click on it to make it bigger. All right. Yep.
The exams on Monday, right?
No, I postponed that because because I feel that it's not fair because I haven't really gone through the whole thing. So it's going to be postponed to at least next Wednesday. I said on Monday that there's a 95% chance, so we'll make it 100% now. Yep.
Will this be updated on the drive so we can see like anything you type in, or the files for the exams? Like if you like try to type in something to explain it, what say those changes?
If I type here, yes, it will be reflected in the version that you see.
Okay.
Yep. Because I just right click on it too.
Okay.
But since I'm the owner, I can make changes to it.
Yeah.
Okay, so it's the question number 3 that is related to the binomial theorem. So in this one, we have 5. So an observer is secret observer because people are not supposed to keep count of things in a casino. So somebody decided I'm going to track and so this person tracked that there are 213 experiments. A sequence is basically an experiment of 5 trials. So there are 213 of these that ends up with 2 heads and 3 tails. And all the other observations were lost because the observer, drank a little bit too much. But there's also a remembering of there are 680 trials. 680 experiments as a total. So of the 680 experiments, 213 ends up with 2 heads and 3 tails, but we lost track of all of the other outcomes. So the question is, how do we know whether the coin is fair or not? And then the second question, which kind of answers the first one too, is how do you assess, whether the coin is fair, and if it is not fair, how do you know the probability of landing on a head? So that's what it's asking. So what do you think? So I'm going to write the answer here so that it is good. This is going to be available to you, as I type. Okay. So we'll answer the first question first. Okay. So the first question, you can say, if the coin is fair, then what is the probability of 2 heads and 3 tails? Okay, so the probability of 2 heads, 3 tails out of 5 trials is going to be, yep. So it's 5 chooses 2, but because it's 0.5 to the power of 2 times 0.5 to the power of 3, right? So that's, that if you look at this number, we can use a spreadsheet to figure this out. So okay, I'm just using the spreadsheet as a calculator right here. So we basically just say, okay, what is combin of 5 choose 2 times 0.5 to the power of 5 itself, because the product is just that. So we end up with a number of 0.3125. Okay, so well, we'll take a look. So this is, oh, it doesn't like to copy and paste that. Okay, is that okay? Since there were 680 experiments, we can expect 680 times 0.3125. Okay, I'm going to use the spreadsheet again to do this calculation. So this number times 680 is 212.5. Okay, so 212.5 experiments with 2 heads and 3 tails. Okay? Does that sound about right? Okay. So our observation is pretty close. Okay, 213 versus 212.5. I mean, you cannot get any better. Because you can have 212, you can have 213, but you cannot have 212.5 experiments, right? I mean, because when you count this, it has to be an integer, it has to be a whole number. Okay. So now for the second question, the coin is indeed fair because the observed frequency of 2 head 3 tails is very close. Okay, as close as possible, is as close as possible to the ideal number. Okay? Yep.
I think we're missing an important question.
Uh-huh.
Who's going to sit there and watch that many coin flips? I mean, that's a lot of coin flips.
Well, therefore that person is drunk in the end. 600 something is not too bad. I mean, it's very boring.
Times 5, you've got so many coin flips there.
Yep, actual flips, yep.
3,000.
I can answer that question. We'll have Sophia do it. I would not be surprised, if people do that. You walk in with Google glasses or some sort of, really covert, video camera, and beams the signal out, and it will be processed, by something in the cloud. And I'm not really sure how casinos can counter that.
They could just search for radio frequency sound coming out from this one. Seems really active.
Do they actually do that?
I mean, no, they don't.
Because everybody has a mobile device now. I mean, everybody has a mobile device. People keep checking their Facebook, Instagram and whatnot. So they have to be able to somehow discern the traffic of tracking their.
So right now, I know you're not allowed to even have a if you go to the casino, you can't have your phone out. You're at like a table or something.
Oh, so no electronics, but only at the table. If you're like having a cocktail, you can probably just take a selfie with the cocktail with, yeah. I think it's pretty hard to enforce those rules. So casinos probably has an interesting future as well, because as electronics gets more advanced, it becomes harder and harder to enforce those rules.
So remember, we don't have secure Wi-Fi anymore.
Oh, that's true.
So you never know, they might have just packet sniffers all throughout the casino and what you're transferring.
Yeah, but there are ways to hide your data in something that is in plain sight. Yep. Mm-hmm. Interesting challenges. All right, so next exam, same kind of question, but the next exam. So I think this is probably the best way to do it, is to focus on one kind of question for all the previous exams, so that we can kind of stay on track with that mentality. So question number 3 again, and once again we are over at a casino, but this time the question is cast a little bit differently. So this time, question A, part A, how would you check whether the coin is loaded or not? You can use formulae without exact numerical values. So in this case, we have 79 experiments ending up with 1 head and 3 tails, and 146 experiments ending with 2 head and 2 tails. I did not keep track of any other type of experiments, nor the total. So this time it becomes the ratio that is the important part. Is that okay? So let me write the answer here. Okay. So you have access to the answer right away because it is in the same document that is linked from Canvas. So that is actually pretty handy. Imagine in the past, in the good old days, where what I write on the chalkboard, you have to really copy everything. That is not the case anymore. Okay, so part A is basically saying the expected probability of 1 head 3 tail given the coin is fair is, I'm just using the spreadsheet equation here, okay, so that you can just kind of copy and paste this into a spreadsheet. So it's going to be, in this case, 4 choose 1, because we have 1 head and 3 tails, and then we have to multiply this with 0.5 to the power of 4, because we have 4 trials per experiment. Yep.
Could you write out Pascal's triangle to figure this out?
Yeah, you could. Do you want me to do it now, or are you asking in the test, can you do it?
I'm just saying, is it possible? Like, is that the idea? Like,
yep. But in this particular question, you can also just give me your equation without giving me an actual number. Yep. So if you do it like this, it is, it's acceptable. Okay. But we have a second number. Okay. The expected probability of 2 head 2 tail is combin 4-2, because we are choosing 4 trials out of 4, 2 trials out of 4 to have heads, times power 0.54, because we still end up with 4 trials. And this is assuming the coin is fair. Because if the coin is not fair, then we can no longer say, oh, it's 0.5 to the power 4, because now it will be p to the power of 2 times q to the power of 2 as well. Q being 1 minus p. Is that okay? Yep.
So 0.5 is the probability of it being heads or tails, which is
0.5 is because when it is fair. Because when it is fair, then the chances of being landing on the head and landing on the tail will be exactly the same. So in other words, p is 0.5, and therefore q is 0.5 as well.
Okay. So if we're doing a different test and the probability is different, that's the number that changes?
Well, the ratio would not work out correctly. Okay, so this is what we'll do. Okay, so we'll give these things specific names. I call this x, and then we'll call this y. Okay. So I would basically say and argue and say that if the coin is fair, then x, the ratio of between x and y should be similar to the observed frequency, which is 79 to 146. So 79 to 146. So that would be my answer. Is that making any sense? So without actually computing the numbers, I'm simply stating how I would evaluate this situation. If the coin is fair, then the ratio between x, y, the two numbers, will be close to the ratio of the observed frequency of experiment outcomes. Does that make any sense? Okay. So since we do have the ability to do the computation, let's figure it out. So in this case, we have x, and then we have y here. Okay, so we'll go back to this test. So x is this equation. The handy part is the equal sign is also here. That makes it very handy. Just like that. And then y also has the, oh, okay. I put the y equals to at the wrong place. So we put it here, y equals 2. And we can also just copy and paste in this case. So we copy and then we paste. So now the ratio, okay, so x ratio y is just this number divided by that number. And then the observed frequency ratio is, let's see, I have to read my own question again because I keep forgetting this. 79 versus 146. So 79 versus 146. They seem to be quite different to me. Okay, it seems like the theoretical number is a bit higher than the actual observed number. Okay, so you can just argue. The more you can, if you cannot come to a conclusion and go like, well, they're kind of off, but I don't know how off is considered really, really off. Then you can just say the more these two numbers differ, the higher the likelihood that the coin is not fair. You can just give me an answer like that. Okay. The important part is the equations. So the important part is not exactly coming to the conclusion or tell me what is the likelihood. The most important part is to come up with this number, and how you would use the ratio between these two numbers as opposed to the ratio of the observed frequency as a part of your evaluation. That is what I'm looking for. Is that okay? Is the rationale explained, or do you guys? Yep, go ahead.
Calculators on their head.
Yes, you are allowed to use scientific calculators, but not the ones emulated on a cell phone. All right, so that's part A. Part B, if you figure out how to check the coin is, whether the coin is loaded, also indicate how you figure out how the coin is loaded. So this time, it is asking, well, now that we suspect that the coin is in fact loaded, how loaded is it? We have the ratio of the observed frequencies, right? So now we have to say, that should match something, right? So now we are looking for something like this, okay? And this time I think I'm gonna use math equations because it is easier to read it in a math equation in this particular case. So we'll try to magnify it a little bit more because that's difficult to see from way back in the classroom. Okay, so what we are really looking at is we're looking at a fraction where we have 4 choose 1. Okay. Okay. Not exactly what I'm expecting. 4 choose. Can you guys see this? Kind of hard. Yeah, it's pretty hard. Okay, never mind. I'm not going to do it this way. So what we're looking for is this number here. We are basically saying 79 divided by 146. If what we observe is truly representative of the nature of the coin, this is really should be the same thing as combin 4 choose 1 times some p to the power of 1 times 1 minus p to the power of 3. 1 minus p being q, divided by combin 4 choose 2 times power p to the power of 2 times 1 minus p to the power of 2. There we go. Yep.
P is a percentage of probability, right?
P is the probability of landing on the head.
So it's going to be less than 1.
It is less than or equal to 1. It could equal to 1 if you have a really strong magnet attached to the coin.
A one-sided coin?
Yes, completely. While the edge of the coin is so bival that it has to, and it's magnetized to land on one side. If it physically lands on the other side, you will see it flip. But this is the second part. Okay, I'm looking for something along this line. Okay, so an equation that basically states, okay, 79 divided by 146 is the observed frequency ratio. Okay, this is fact. This is what we actually saw. But it should be consistent with the theoretical number. So the theoretical number corresponding to the 79 is this number here, because this is the probability of observing one head, 3 tails, given that the chances of landing on the head is p, and therefore the chances of landing on the tail is 1 minus p. Okay? And divided by the other probability, which is the probability of having 2 heads and 2 tails, because this is based on the binomial theorem that explains, oh, okay, if we have 4 trials and we want 2 of the 4 trials to be heads, this is the probability, assuming that p once again is the probability of landing on the head. Is that okay? So once you solve for p, which you don't have to, because in this question, if you can get to this point, I'll give you full credit already. So you don't actually have to solve for p. But solving for p is not really that difficult, because you basically have there's enough information to solve for p. I'll just put it that way. Is that okay? Yep. Mm-hmm.
Why is it that you do the 1 minus p at the end?
Because that is q. That is the same thing as the chances of landing on the tail.
Oh, okay.
Yeah. So this part is basically the component that accounts for landing on the tail 3 times. And this is accounting for the and landing on the tail twice out of 4 trials. Is that helping? Okay, cool. All right, so that answers part A and part B. Part C is assuming the observation is okay. So that answers part C and part B as well. So this one single equation answers both of those. Oh, okay. I do have to say, whether heads have a higher probability or tail have a higher probability.
Oh.
You can probably tell.
No,
so you have to solve it. Yep. So to solve this one, let me see. Yeah, there's enough information to solve for it, but you don't really have to solve the entire thing, because you just have to answer the question of whether heads have a higher probability or tails have a higher probability. So by looking at the ratio, what do you think? Huh?
Like tails is higher probability.
Tails have a higher probability. You can always push the argument to the extreme where one is 0 and the other one is 1, and then you just look at the observed frequency and see which end it is closer. So that's the quickest way to kind of evaluate, is it the tail that has a higher probability, or is it the head that has a higher probability? basically assign the head, probability of landing on the head to be 1, figure out the ratio, and then assign the opposite way, where the tail has a probability of 1, and then look at the observed frequency and see which end it is closer to.
But if we assign a head of probability 1, all these other it's like sort of like the limit as it approaches 1, you mean? Because if it was actually 1, then we wouldn't be able to get any tails ever.
Okay, if P is 1, then this is just 1, and this part becomes 0, right?
Yeah.
So we basically are looking at, just combine 4, 1,
Yeah.
which is
Times
how many
0.
ways can you choose one thing out of 4? 4, right?
Yeah.
And then this one is 4 chooses 2, which is 4 factorial divided by 2 factorial times 2 factorial. So that would be 24 divided by 4, which is 6. So, and once again, because this is 0. Wait, something is not right. Something is not adding up. Because if one probability is 0, oh, that's right, it does work out. Because of the, it cannot be all the way to 1 and 0, but it can be close, right?
Yeah.
You're correct. You're taking the limit, not the entire way. Because the entire way means, 1 would turn into 0, so you have a 0 divided by 0, which is a problem. Okay. So are there any questions about this? Yeah. Okay. All right. So let's look at the third exam, which also has a question similar to this one. There are only so many ways I can ask, a question to test for a particular concept. Okay, I think it is still question number 3. So let's check out. Oh, this one does not have a. Nope, this one doesn't have a casino problem, but it does have a guitar playing problem, which is not exactly the same as a coin tossing problem, but it is similar. Okay, so let's look at this one and see if we can solve this problem. So question number 3, this one is still based on combination and permutation, so it is something that we should know how to solve already, but we'll give it a try. So the question is asking, let me see, am I cutting off anything here? Just a little bit, there we go. So we have 12 students out of 37 in CISP who play the guitar according to an anonymous poll. 7 students sitting in the front row, 7 students are sitting in the front row. And I'm asking what is the probability of, out of the 7 students in the front row, 3 of those are guitarists. You can leave it as an expression if you don't want to compute the actual combine and permutation of stuff, but make sure that you show your reasoning and also the derivation of the expression. Okay. So how do we approach this? This is related to the lottery problem, by the way. Okay. So how does this relate to the lottery problem? Obviously, there's no prize money, right? There's no jackpot here. Yep.
It's the combination of multiple probabilities together. That's the final answer. That's
Okay.
you need at least, it's 7 choose 3, then you need 7 choose 4, 7 choose 5, 7 choose 6.
Yep. Mm-hmm. But on top of that, there's something else, because a probability is always the frequency of a particular event or the cardinality of the event set divided by the cardinality of the omega. Okay, so the first question is, what is the cardinality of the omega in this case? In other words, how many ways can I choose 12 out of 37 students who play guitars, who play guitar?
37 choose 12.
Okay. All right, so omega is the set of all possible ways of assigning 12 students out of 37 who play guitar. Does that make any sense? That's my entire outcome, okay? because that's given to me. I know already that there are 12 students out of 37. So in this case, should I use permutation or should I use combination? So you can imagine you have a set of 37 items, right? 37 students. And the question is, how many ways can I pick 12 elements out of the 37?
37, take 12. Choose 12.
Chooses, exactly. So because the order is not important. Okay, I can choose, well, Jake is absent today, so we'll pick on him. So I can pick Jake as the first out of the 12 people, out of the entire class. I can choose him as the second person. I can choose him as the last person, the 12th person. Does it make a difference? Nope. So that means ordering is not important. Okay? So this means the cardinality of omega is the the number of combination of 37 choose 12. Okay. So knowing the cardinality of omega is really helpful. So now we need to look at the outcomes where at least 3 out of the 7 students in the front row are guitarists. So now you have to think about the lottery problem, because this is almost the same thing as having 12 lucky numbers and 27 non-lucky numbers. Remember in a lotto, you have 5 lucky numbers out of 69, which means the other 64 numbers are not lucky numbers. So this one is really asking, okay, the first scenario is we have exactly 3, okay, 3 out of 7 in the front row. But in this case, you have to remember to deal with this, you are basically saying, okay, we'll choose amongst the 12 guitarists, we are choosing 3 out of those 12. Okay, that way we can have the 3 guitarists. But you have to remember that we are also choosing of the remaining portion. We're choosing the remaining portion of the front row people. There are 4 of them out of 37 minus 12. So this is the number of ways I can choose 3 out of the 12 guitarists and 4 out of the 25 non-guitarists to be on the front row. Is that making any sense? Is that okay? Yep.
Since it's saying at least, won't you have to do this calculation multiple times?
Oh, yep, exactly. We have 4 out of 7, which is combin 12-4 times combin 25 out of 3 this time. And then we have 5 out of 7, which is combin 12-5 times combin 25-2. And then we have 6 out of 7, combin 12-6 times combin 25-1. And we have the last one, which is 7 out of 7 students in the front row are guitarists. So we have choose 7 out of 12 times combin 25-0. So when you add up these, it becomes the numerator of the probability. You divide it by the by combin 37-12. That becomes the answer. But this is also why I said in this case you have to you may leave your answer as an expression, even as a sigma. Okay, because if you use a sigma, it is a little bit easier to express because you can just say that I goes from 3 to 7, and then just specify the actual expression that changes with I. So that would be the quickest way to express your answer. But I don't need you to actually find out the actual numbers, because that's the job of a spreadsheet, not you. But is that okay? I mean, does everybody, can you guys relate this question back to the Powerball lottery problem that we talked about in class? Yes, you sort of. Yep.
So like omega is all the ways you can pick those 5 out of the 60 something.
No, omega is all the ways that I can choose 12 people out of 37 as guitarists.
Yeah. I was talking about lottery, sorry. Like when you said the 5 lucky numbers.
So in the case of lottery, not counting the Powerball, so we'll take the Powerball out of this whole thing because it's independent to this particular problem. So in that case, we are choosing 5 lucky numbers out of 69, and then the remaining 64 are not lucky numbers. Question?
I was going to say this is basically saying what are the odds of us getting 3 or more lottery numbers.
Yeah. Yep. Exactly. It is equivalent to that problem, but without factoring the Powerball number, which is entirely not here. Okay. So it really is testing whether you can relate a problem, phrased this particular way, with problems that we have already solved in class. Is that okay? All right.
Why couldn't we say that, like, the probability of any one student playing the guitar is 12/37ths, and then do like the sum from I equals 3 to 7 of 7 take. I wish I could write up there, but you know what I mean. So we're doing what we did before with the coins, where we have like the probability. We have like heads, tails, but in this case we have sort of the guitar. I don't know how to say this in words.
If you want to, you can use the whiteboard.
So, okay.
Okay.
So, why can't we do, so like 12/37 is the probability of someone having playing a guitar, and so we take the sum from I equals
3
to
7
to 7 of I choose, what was it? 7 choose I.
Okay.
7 choose I times 12 divided by 37 to the I, and then the other probability 25, 37.
Because the way you set it up
Okay.
is only going to work if it is with replacement.
Oh, okay. Oh, okay.
Yep.
Okay. Sorry.
Yep. But that's a good question to ask, But when you look at something like this, okay, 12 people are guitarists, 37 out of a total of 37. The moment you raise this to a power of something, is basically saying, the chances of the first person being a guitarist and the chances of the second person being a guitarist are the same.
Yeah.
But because it is without replacement, it is actually not the same.
Okay.
So that's that's the reason, that's the rationale of why this is the answer and not that.
Okay.
Yep. All right. Any questions about this one, number 3? Okay. If there are no questions about number 3, I'm going to go back to. Okay, I might have this already. Okay, here. So I did add a section here, in section 5, because that is what you need to do with the a transmitted bit you received incorrectly. So this is really just a formalization of the reasoning of that stuff. So let me go back to the question itself, because I think it's better to read the question itself. All right, so when you read the question, the first question particularly, the first question of all 3 tests that we have looked at, they're all based on a transmitter-receiver configuration where a 1 can be received incorrectly as a 0, and a 0 can be received incorrectly as a 1. Okay, so we have to so in my notes, the extension of the notes, I use this to represent the omega 1 is basically all the possible outcomes where a 1 is transmitted, but it can be received as a 0 or 1. And 1, 0 is a particular element of omega, because it is a 1 being transmitted but received as a 0. It's just a way of representing it, okay? But the bottom line is, the last part here, the bottom line is the probability of a 1 transmitted and received as a 1, and a 0 after that transmitted as a 0 but received also as a 0, and a 1 transmitted but received as a 0, and a 1 transmitted but also received as a 1, the probability of this is really the product of the probability of a 1 transmitted received as a 1, the probability of a 0 transmitted and received as a 0, the probability of a 1 transmitted but received as a 0, and the probability of a 1 transmitted and also received as a 1. But these individual probabilities are not based on cardinality anymore. In other words, we are not just looking at the cardinality of this, which is a single element, versus the cardinality of this, and just look at the ratio and call that the probability, because now we are actually observing experiments and say, okay, if I transmit a 1, 10 million times, how many of those times is it going to be received erroneously as a 0? Okay, it is just empirical. Is that okay? Okay or not? Okay. So 1011 is transmitted. Okay. So when this 1 is transmitted, there's a chance that it may be received as a 1, there's a chance that it may be received as a 0. Okay, so let's say 0.9 versus 0.1. This is 0.9, this is 0.1. Okay? When a 0 is transmitted, there's a chance of, let's say 0.8, that it is received correctly as a 0, a chance of 0.2 that it is received incorrectly as a 1. And then this is another one, which is 0.9 again, 0.1 again. So I'm basically looking at this and say, when you transmit a 1, there's a 90% chance it is received correctly. When you transmit a 0, there's only a 0.8 or 80% chance that it is received correctly.
Is it always the same?
Yep. So this is making one big assumption, as you said, okay, that each bit transmitted and how it is received is independent to the rest of the trials. It is independent to what goes before, it is independent to what goes after. Okay? So now the question is, if I'm receiving 1011 transmitted, but I'm receiving it as 1001, what is the probability of that? So you have to look at each individual probability, which is 0.9 times, this is 0.8 times, this is 0.1 times, once again, a 0.9. So the product of each probability becomes the probability of the entire outcome. That's the whole point. Is that okay? So the notes here, in my fine tradition, is definitely making the notation a lot harder to understand than the actual concept itself.
This was on one of the other tests previously.
It is in all 3 practice tests, but in various forms. Yep.
Can you go back to the question?
Sure. Yep. There we go. So this one is particularly interesting because this one is a little bit different from the other tests. It's still asking about the same thing. So this one, we're running out of time, so we kind of have to be mindful of time. We have 2 minutes left. In the transmitter and receiver configuration, it is known by experiment that the chances of correctly transmitting and receiving an entire packet with 1 million bits is p. So this one is saying, okay, you may assume the probability of 1 transmitted and received as a 0 and the probability of a 0 transmitted and received as a 1 are the same. So in this case, it is symmetric. So we are looking at point, xy, 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 for all bits transmitted. Okay. Furthermore, the probability of transmitting and receiving a bit incorrectly is independent to all other bits. So it doesn't matter that you have transmitted, like 10 ones already. Okay, the chances of the next bit being received incorrectly stays the same. Is that okay? So the question of part A is explain and derive the expression of a single bit transmitted and received correctly. And I'm missing something here. It is known by experimentation that the chances of correcting, okay, that's P. Okay, so you have P and 1 million to work with. Those are the two numbers given to you. Okay, we transmit 1 million bits, and the chances of receiving the entire packet correctly is P. And the question of part A is asking, what about a single bit being received and being transmitted and received correctly? Yep.
Would be something to the power of 1 million?
It would be power P it is taking the root of a millionth.
What number is that?
Huh?
What number is
Oh, this is all you need to, as an answer.
Just mean like what is equal to that?
So that means if P itself is 0.8, okay, so let's say P is 0.8, which means, if you transmit a million bits, there's only 80% chance that you receive all 1 million bits correctly. Then the chances of one single bit being received correctly is 0.8 to the power of 1 millionth. Yep.
So we could just, instead of putting 0.9 or 0.1 and all that, we could just say if it works, it's X, if it doesn't work, it's Y.
Right.
If they all work, it'd be like X to 1 million.
Yep.
And if, for like the next part B, it would be X to the 999,999 plus X to the whatever.
Right. Yep. So part B is to basically asking, explain and derive the expression of the probability of a 1 million bit packet containing 1 to 3 error bits. So that's exactly what you said. Now, but because the position is not specified, so it becomes a combing problem. It's 1 million chooses 1, and then you have 999,999 as the bits being received correctly. So so you have to raise P, or not P, but whatever this probability turns out to be, let's call this X, okay? So you have to say X to the power of 999,999 times 1 minus X to the power of 1. And then the combing is going to be choosing 1 out of a million. And then the second one is choosing 2 out of a million times times X to the power of 999,998, and then times 1 minus X to the power of 2, and then the third one is kind of similar in the format. So this one is strictly, there are no real actual numbers. It's really just a mind, exercise to see whether we can derive the equations correctly or not. Okay, all right. So this is where we stand right now. Obviously Monday will be a continuation of this. Okay, but hopefully you have time to kind of review all the material today.